If you're taking a general biology class, usually one of the first topics you'll get to is water. And there's a lot to learn about water, but pretty much everything comes back to the structure of the molecule. So it's really important to have a good foundation on the molecule structure. Hi, I'm Sarah, and I'm your other biology professor, and let's talk about water structure. All right, welcome to water. In this video, I'm going to give you a quick review on the structure of a water molecule, and then we'll do some practice to make sure that everything's clicking. If you're watching this video, it's probably because you want to look at the structure of a water molecule, right? Either because you are totally lost, or maybe you're feeling okay, but you just want some review. But either way, let's take a look. H2O, we've got 2 hydrogens and an oxygen atom. Let's bring them together and make some water. Our water molecule is put together through the sharing of electrons between oxygen and hydrogen, and the sharing of electrons between oxygen and the other hydrogen. So these are covalent bonds. Bonds generated through the sharing of a pair of electrons. So in each pair, one is coming from hydrogen and the other electron is coming from the oxygen. A water molecule has a bit of a bend to it, like so. It's got a bond angle here of about 104 degrees, 104.45, something like that. I'm not going to get into geometry of molecules here, but that has to do with the repellent forces of these 2 lone pairs of electrons repelling each other and repelling those 2 shared pairs of electrons as well. In our 2 covalent bonds, we have electrons being shared between oxygen and hydrogen, but are they being shared equally? Well, to know that, we've got to look at electronegativities of the 2 atoms involved in the bonds. Electronegativity is the tendency of an atom to attract shared electrons. The more electronegative that atom is, the more the electrons in the shared pair are going to want to spend time near that atom's nucleus. They're going to spend less time around the other atom's nucleus. Here, oxygen is more electronegative than hydrogen. So in each of our covalent bonds, we've got shared pairs where one electron comes from the oxygen, one comes from the hydrogen. Those electrons are going to spend a little bit more time hanging out on the oxygen side of the bond. That's going to give oxygen a partially negative charge, right? Electrons are negative, and if they're spending more time around the oxygen, their negativity is spending more time around the oxygen, giving oxygen a partial negative charge. And that's the case for both of the bonds in our water molecule. We can represent these partial charges on our diagram by using the lowercase of the Greek letter delta. I'm absolutely terrible at drawing these deltas. It's like a character flaw of mine. So, look in your book. You'll see some good examples of what it should actually look like. But anytime you see it, you can just read it as partial. If our oxygen is getting partially negative charges because the electrons are spending more time over there with the oxygen, what's happening at the hydrogen end of our water molecule? They're enjoying a little bit less time with those shared electrons. So a negative aspect, those electrons, is away longer, taking its negativity with it. And so our hydrogens are going to take on partially positive charges. In this water molecule, with our covalent bonds, our bond between an oxygen and a hydrogen, got 2 of them, right? We've got partially negative charges on the oxygen side of the bond, partial positive on the hydrogen side of the bond. So we've got an unequal distribution of charge across the bond, which means we can now say that we don't just have covalent bonds, we have polar covalent bonds. Because oxygen is more electronegative than hydrogen, electrons are going to spend more time over by the oxygen, and that gives us an unequal distribution of charge across our covalent bond. So we've got polar covalent bonds in the water molecule, but we could also describe the molecule itself as a polar molecule. The oxygen end of the water molecule is partially negative. The hydrogen end, partially positive. So we've got an unequal distribution of charge across the molecule. We've got a partially negative end and we've got a partially positive end. We have poles. So not only does water contain polar covalent bonds, where the charge is unequally distributed across each of those two bonds, but the water molecule itself has an uneven distribution of charge. So it's polar too. You can make so many test questions dealing with the partial charges on a water molecule. Trust me, I have made plenty. So let's do a little bit of practice to make sure that all of this is sinking in. So I've drawn up 4 different water molecules. They look a little bit different from what we just saw, but there's a lot of ways to draw water, so you should be prepared to see different types. We've got 4 water molecules. I've thrown some partial charges on these water molecules. Only one is correct. Which one? Pause the video and take a look. All right, did you get it? Hopefully you went for option D. Partially negative charge on our oxygen, partial positives on each of our hydrogen. All of the other options have at least one charge that's incorrect. Let's try one more example, and then I'll give you some tips on how to remember these. I know this is a water lesson, but we're looking at carbon dioxide here. So we've got carbon double bound to 2 oxygen atoms. So why is this a good example to compare with water? Well, just like in water, we've got a molecule that is made up of 3 atoms. We've got a central atom covalently bound to 2 other atoms of the same type. Now, CO2, you'll notice, is linear. It's a straight molecule, and that's just because of the lack of lone pairs on that central carbon. Now, the electronegativity of carbon is similar to the electronegativity of hydrogen. So with that in mind, would you expect these bonds to be nonpolar covalent or polar covalent? Hit pause if you need to think about it. All right, got it? You realized that these would be polar covalent bonds. Why polar covalent? Well, I told you we were going to look at another example dealing with partial charges, so that was probably a pretty good clue. But remember with the water, oxygen's more electronegative than hydrogen, resulting in that uneven sharing of the electrons in the bond, and it's a polar bond. And I told you, carbon's electronegativity is similar to hydrogen's. So you're going to get the exact same dynamic in the oxygen-carbon bond as well. So with that in mind, let's throw some partial charges up on this bad boy. All right, so who's getting the partial negative? That's going to be the bond participant that is more electronegative, and that is, of course, oxygen, just like what we saw with water. And that's true for both of the oxygen-carbon interactions here. And that means that carbon is going to get the partial positive. All right, so that gives us another example of how electronegativity differences influence the type of bond that we have, polar covalent, which in turn is going to generate partial charges. Now, if your brain breaks on you, which I know can happen sometimes during a test, when you're thinking about the partial charges on the water, try to remember that if you write an H, you can kind of make little plus signs inside it. So hydrogen is going to get the partial positives. Stupid tricks like that can help me sometimes, so maybe it's useful for you too. And one more trick, and I swear I don't remember learning this in school. I probably did and just forgot. But when you're looking at the names, the way that the formula for a molecule is written, so CO2, H2O, the standard convention is to write the more electropositive element first. Electropositive means less electronegative. That's going to be the less attractive one for electrons. So you can see CO2, got the carbon first. H2O, we've got the hydrogens first. Those are our less electronegative, more electropositive elements. Those are the ones that are going to take on the partial positive charge in our polar bonds. Thanks for watching. I hope you feel like you've got a really great foundation on the structure of water, and you can tackle some of those higher level concepts dealing with water now. Be sure to give the video a like if you found it helpful. Check out my website for more videos on biology topics, and I'll see you next time. Bye.